Hello students and welcome to Chemistry B. I'm Ms. Sleight and today I'm going to talk a little bit about how my chemistry class is going to work, and I'm also going to go over a review of Chem A. If you had me for Chem A, you can skip to the time listed below to go straight to the review. So my chemistry class is going to work a little bit differently than some of your other classes. Instead of doing our notes and lecture in class, that's what your homework is going to be. So in class, we're going to be doing activities and practice problems and group work and labs. Your homework is most nights you're going to be assigned a short video, YouTube video to watch and take notes on. The videos are all linked to my website, which I'll be showing you how to get to in a moment. If you ever find that you do not have reliable internet access at home, please let me know and I will get you a hard copy of all of our notes. So let's look at the website for a little bit. So if you were to scan the QR code that is found on your syllabus, it will take you here to my class website, Sleightium. All of my classes are listed at the top of the screen. We're Chemistry B, so that's what we're going to click on. If you go to the main page for Chemistry B, here you're going to find a Google Calendar that has everything that we're doing each day, as well as what days different note videos will be assigned for you, as well as dates for tests and when long Kappa is due. If we go, you will also find here on this page a button that will take you directly to the login page for long Kappa. If we go to a page devoted to a particular chapter, you'll find that there'll be a list of videos and links. As you can see, I'm still in the process of building some of these, but the videos will go up as we get them. And you will also see links to all of your assignments. And at the bottom is the list of learning goals for the chapter, so these are the things that you're going to be tested on. So when you're assigned a video for notes, you're just going to come here, click on the video link, it'll take you to that, and you're going to take some notes on it. You can also follow this link on how to take notes if you feel like you need some help with that. Because I'm not going to be giving you guided note packets, you're going to be taking your own notes from scratch. It's good practice, especially if you're planning on going to college. So now let's do some review of Chemistry A. Alrighty folks, there are really only 3 main topics from Chemistry A that we really need to know well to be successful in Chemistry B. And that is significant figures, dimensional analysis, and naming chemical compounds. We're talking ionic, molecular, and acids. So those are the things that we're going to talk about right now. We're going to start with significant figures. So for significant figures, there's a variety of different ways to think about these rules for what is significant and what isn't. A really interesting way that you might not have seen before is to think about it in terms of a Venn diagram, where on the left we have significant, on the right we have not significant, and then we kind of have our special cases in the middle. Things that are always significant. Non-zero numbers. Zeros in the middle of non-zeros numbers. Like if we're talking about something like 101, that's a 0 in the middle that's significant. Things that are never significant, leading zeros, or anything that's just a placeholder. The things in the middle are zeros at the end. That's where it can get tricky. So zeros at the end, it depends on whether there's a decimal point involved. So if there's no decimal, Our zeros at the end are not significant. So things like 500, 50, 12,000, all of those have zeros at the end that are not significant. If there is a decimal point involved, then your zero at the end is significant. So things like 50.0 or 500 just followed by a decimal point, or 0.100. All of those have zeros that are significant. So that's just how to know if something is significant. The big reason that we care about sig figs, though, isn't necessarily so we can just count the significant figures in a number. It's so that we know how to round our calculations to the correct amount of precision. So these are the big rules that we really, really need to know. So for multiplication and division, you're going to round your answer to the lowest total sig figs. If we're dealing with addition or subtraction, on the other hand, addition and subtraction, you're going to round to the least precise measurement, which typically means your fewest number of decimal points. And really, these two rounding rules are what we really need to know about sig figs, because we need to know that in all the calculations that we do in Chem B, that we are appropriately rounding our final answer to the correct number of significant figures. All right, now let's take a minute to talk about dimensional analysis. So if you had me for Chemistry A, you might have remembered me telling you that we didn't really learn how to do dimensional analysis because it's the best way to convert metric units. Because it's not really the best way to convert most metric units. We learned dimensional analysis so that we could use it in Chem B for more sophisticated calculations. So we need to remember how to do it with more basic things like metric conversions so that we are then going to be able to apply this to more sophisticated calculations when we talk about stoichiometry. So when we do dimensional analysis, we want to have our handy dandy friend, the metric conversion table, with us. Because again, nobody really needs to be able to memorize all these conversions. We can just use this chart to help us. So make sure you have this handy with you. Let's do some examples, because that's the best way to do this. Let's say our example is convert 5.2 kilometers to meters. Well, first off, I need to look at what the conversion factor between kilometers and meters is. If you look at your chart, it tells us 1 kilo, 1 kilometer, is equal to 10 to the third base, meaning the base unit, which in this case is meters. We can write this conversion factor as two different ratios. We can write it as 1 kilometer over 10 to the third meters, or as 10 to the third meters over 1 kilometer. What I need to figure out is which one is going to let me convert and cancel my units of kilometers to give me meters. So if I'm starting with 5.2 kilometers, which one of these is going to allow me to cancel units of kilometers and end with meters? Remember, to be able to cancel things, the units have to be on top and bottom. So that is going to be this conversion factor. So I'm going to multiply by 10 to the third meters over 1 kilometer. Now we can see units of kilometers cancel, and I end with an answer of 5.2 times 10 to the third meters. Now remember, when you're just doing dimensional analysis, your Your number of significant figures should never change because conversion factors, we assume that they have an infinite number of significant figures. This isn't the only way to solve these type of problems though. You can also set it up as equivalent ratios and just do some cross multiplication. So for example, I could do this same problem in a slightly different way. I could say, I know that in 1 kilometer, there's 10 to the third meters, but I want to know how many meters are in 5.2 kilometers. Well, again, these ratios have to be equal to each other, so I can just do some cross multiplication, and I will still get an answer of 5.2 times 10 to the third meters. The only slight downside with using this method is it's not as clear what units you should end up with at the end. So you really need to make sure you're keeping a close track of that. Let's do some more examples. Let's say we have something a little bit more complex. Let's say they ask me to convert 230 centimeters to kilometers. Well, if we look at our chart, we don't have a straight conversion factor between centimeters and kilometers. We can see that 10 to the second centimeters equals 1 meter. And we can see that 1 kilometer equals 10 to the third meters. So what we're going to have to do is we're going to have to do 2 steps here. We're going to have to convert from centimeters to meters, and then from meters into kilometers. And there's, again, a couple of ways you can do this. There's a longer way where you can separate each step, or you can kind of condense it all into one, and I'll show you both of those. So I'll take my 230 centimeters. Again, I need to multiply this so that centimeters cancel and I end up with meters. So that means my 10 to the second centimeters go on the bottom, my 1 meter on the top. When I do that, I'm going to get 230 times 10 to the negative second meters. Now, I know this isn't in correct scientific notation right now, but I'm going to wait until I get to my final answer to change it into correct scientific notation. It's just going to save me a little bit of work. Now that I have meters, again, I need to multiply by a conversion factor again. This time, I need to cancel my meters, so that needs to go on the bottom, or my 10 to the third meters, and my 1 kilometer needs to go on the top. So meters will cancel, and this time I'll end up with 230 times 10 to the negative fifth kilometers. Last thing I'm going to do is I'm going to put my answer in correct scientific notation. So I'm going to move my decimal 2 places to the left. That's going to increase my exponent by 2. And so my final answer will be 2.30 times 10 to the negative third kilometers. Now, let's say you wanted to do this, but you want to condense your work a little bit. Instead of splitting it into 2 parts, you can just set the conversion factors side by side. So you could also do this where you have 230 centimeters multiplied by my first conversion factor, 1 meter over 10 to the second centimeters. Centimeters are canceled. And then immediately go straight into my conversion factor to kilometers. 1 kilometer is 10 to the third meters. Boom, boom. I've canceled all of my units except kilometers. And you would end up with the exact same answer, 2.30 times 10 to the negative third kilometers. So it's all about canceling units and practicing. Again, if you find that you struggle with this, I would always write down the 2 choices you have for a conversion factor. Because remember, if we take something like my centimeters to meters, we can have 10 to the second centimeters over 1 meter, or 1 meter over 10 to the second centimeters. We selected this conversion factor to use right here. Why did we select that one? Well, because if I took this one, centimeters wouldn't cancel. You gotta have the units on top and bottom to make them cancel, just like in algebra. I know that went kind of fast, but we're gonna do more practice problems on this in class. Now let's talk about the really big topic that's gonna be important and necessary right away with the very first thing we're doing in Chem B. Let's talk about naming compounds. All right, now let's talk about ionic compounds. Now, one of the most important things when we're naming compounds is we need to be able to know the difference between them. We need to be able to look at a formula or look at a name and know whether it's ionic, molecular, or an acid. The big giveaway for ionic compounds is that they're composed of metals and nonmetals. So if you see a metal with some nonmetals, that's your cue that it's ionic. Now, when we're writing the names and the formulas, we got to know about the charges because ionic compounds are made of ions. So this is where having your periodic table out, knowing valence electrons, knowing how many they'll gain or lose is going to tell you the charges. And most of that can be determined straight from the column numbers. We talked about this a little bit more in depth in class. The thing to remember with your transition metals and your other metals is that they form multiple ions, with the exception of zinc, cadmium, and silver. So anything other than zinc, cadmium, and silver, its name is going to tell you something about its charge. So let's just dive right in and do some examples. Let's start with the easy thing. Let's start with going formula to name. So let's say we start with these three examples. We've got MgCl2, we've got SnO2, and we've got CaCO3. All right, so first thing, Mg. You pull out your periodic table, you'd find that it is indeed magnesium. So we're just going to write the name of that first element. Boom. Magnesium is not a transition metal, so we don't need to do anything special about indicating its charge. We can just leave it as its name. Then I'd find Cl. Cl comes from chlorine. We're always going to change the ending of that second element, though, to IED. So chlorine is going to become chloride. And that's all there is to it. Let's look at SnO2, though. Sn, though, you find it on your periodic table, it's tin. Tin is one of our other metals, which means it can form multiple ions. So we're going to need to indicate its charge using the name. Now you could use the traditional system where the ending put on the Greek name changes based on whether it's the higher or the lower, but honestly the traditional naming system is not used commonly anymore at all. The stock system is almost exclusively used for naming ionic compounds, so that's what I'm going to show you. And the stock system uses Roman numerals to indicate the charge of the ion. So I'm just going to leave a space for those Roman numerals. O is oxygen, which we're going to change and make oxide. So how do I figure out what the Roman numerals are? Well, the Roman numerals represent the charge of the ion. So if we look at the formula, we've got one tin ion, and it is combining with 2 oxide, because that's where the O2 comes from. If we pull out our periodic table, we can see that oxygen has 6 valence electrons, which means it's going to gain 2 to form a -2 ion. So each of my oxides have a -2 charge. Well, ionic compounds are always going to combine so that they form neutral compounds. So all of my charges have to add up to 0. The only way I can have charges add up to 0 is if my tin has a +4 charge. So then that means my Roman numerals are a 4, tin 4 oxide. Next up we have CaCO3. Well, Ca is calcium. Calcium is not a transition metal or another metal. We don't have to do anything fancy with Roman numerals. CO3, though, there's more than one element present there, meaning this is a polyatomic ion. So this is where we need to pull out our polyatomic ion chart, which you'll see CO3 is right here. Its name is carbonate. All I got to do is write the name carbonate now. Oops. Carbonate. And that's how you would write the name. So going from formula to name is pretty easy. However, what you're going to probably have to do most of the time when you're writing chemical equations is most of the time you're going to be doing the opposite, which is a little bit trickier. So let's look at what we've got to do to go from name to formula. So let's start out with some examples. Let's say we've got iron 3 oxide. Let's say we've got sodium sulfate. Let's say we've got calcium hydroxide. All right. Let's start looking at these ones now. So iron 3, remember that Roman numeral is telling us the charge of the metal. So it's telling us my iron is a positive 3. Oxide, again, we looked at before. It's got 6 valence electrons. It's going to form a negative 2 ion. Now this is not a neutral compound. The easiest way to figure out what would make it neutral is ask yourself, what's the lowest common multiple between 3 and 2? Well, the answer is 6. So to make this neutral, I need a total positive charge of positive 6 and a total negative charge of negative 6. Well, to get negative 6, I'd need 3 negative 2 ions. And to get positive 6, I'd need 2 of my positive 3 ions. So when I write this, we'd write the symbol Fe for iron. I have 1, 2 iron ions, subscript 2. Symbol for oxygen is O. I have 1, 2, 3 oxide ions, subscript 3. Next up, let's look at sodium sulfate. Sodium, well, we got to look at the periodic table. Sodium's a part of group 1, so it's going to lose a valence electron to form a positive 1 charge. So I know sodium is going to be a positive 1. Sulfate, ATE, is our hint that this is a polyatomic ion. So if we look at this, sulfate is SO4 with a negative 2 charge. So what that means is that you've got a sulfur bonded to 4 oxygens that altogether has a negative 2 charge. Well, that's not neutral, right? To make it neutral, we need another one of our positive 1 sodiums. So I've got 2 sodium ions combining with 1 sulfate. So I'd write Na, that's my symbol for sodium. I needed 2 of them. And then sulfate is SO4, and I only needed 1 of them. Lastly, let's look at calcium hydroxide. Calcium's a part of group 2. It's going to form a positive 2 ion. Hydroxide is another polyatomic ion. So we'd pull out our sheet, we'd look for the name hydroxide, and it's right there. Hydroxide is OH with a negative 1 charge. So that's like having an oxygen bonded to a hydrogen, altogether negative 1 charge. Now this isn't neutral, right? We need another hydroxide, another hydrogen bonded to an oxygen with a negative charge. So when I write this, I'd have a Ca for calcium. Now I need to show that I have 2 hydroxide ions. Anytime you have multiple of a polyatomic ion, you need to put it in parentheses. So I need to put my OH in parentheses and then a 2 on the outside. If you don't put it in parentheses, it's not going to be correct. Because if I just wrote it as CaOH2, well, that's not even the same number of atoms, so that doesn't work. And if I wrote it as CaO2H2, well, now you don't see the hydroxide ion in there anymore, so it doesn't match the name. This is the only correct way to write calcium hydroxide's formula. And that's basically the crash course on ionic compounds. They tend to be the trickiest, so when we talk about acids and molecular compounds, it'll go a little bit quicker. Our distinguishing feature about molecular compounds is that a molecular compound is going to be composed entirely of non-metal elements. So anytime you see all non-metals, that's your cue that this is a molecular compound. Also, if you're looking at a name, molecular compounds use Greek prefixes to indicate the number of each element in a particular formula. So if you ever see any prefixes in a name, that also automatically tells you that it's a molecular compound. So let's talk about what are our Greek prefixes. Well, one is mono. Thing to remember here, though, is that mono is a prefix that's only used on the second element. So if you only have one of the first element, you're just not going to put a prefix on it. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca, and you're not really going to need any prefixes higher than that for this. We're also going to be changing the ending of our second element to IDE, just like we did when we wrote ionic ones. So let's just go through some examples. Let's say I've got N2O. Let's say I've got CF4, and let's say we've got di-nitrogen pentoxide. That looks pretty good. All right, N2O. Well, prefix for 2 is di. N is nitrogen, dinitrogen. We have just one O, so it's going to need the prefix mono. And O is oxygen, so we're going to change it to oxide and make it monoxide, dinitrogen monoxide. CF4, there's no prefix, there's only one carbon there, only one C, but mono is only used on the second element, so we're just going to write carbon. F4, well, our prefix for 4 is tetra, and F is fluorine, which we're going to make fluoride. Boom, carbon tetrafluoride. If you got to go the other way, it's just as easy. Dinitrogen pentoxide. Well, nitrogen has the symbol N. Di means there's 2 of them. Oxide, symbol for oxygen. Penta, that means there's 5 of them. N2O5. All you need to know for molecular compounds is those prefixes. If you've got that down, you're good to go on these. Now let's talk about acids. The way that you're going to be able to figure out something is acid is it's going to be hydrogen bonded to some negative ion. There's 2 types of acids. There's binary acids and oxyacids. You need to be able to know the difference between the 2 because they are named slightly differently. So let's start with binary acids. A binary acid is just hydrogen plus one other element. So, for example, things like HCl, HF, HBr. So when we go to write the name for a binary acid, it always starts with the same prefix. It always starts with the prefix hydro. Then you're going to include the root name of the anion. So in this case, our anion is chloride. So we're going to include the root chlor. And you're going to end with the suffix IC and add the word acid. So hydrochloric acid is HCl. We can do this the same with these other two. HF, it's going to start with hydro. Our anion is fluorine, so we're going to make it fluor. Add the suffix IC and acid. Hydrofluoric acid. HBr, start with the prefix hydro. Bromide is our anion. So the root is brome. Add the suffix IC, the word acid. Hydrobromic acid. So the one way you can tell that it's a binary acid from the name is if it has the prefix hydro. If you see the prefix hydro, you know it's a binary acid. That means it's going to be hydrogen plus just one other element. And look at the root in the name to know what that other element is. The other type of acid is an oxyacid. And an oxyacid is hydrogen bonded to a polyatomic ion that includes oxygen. Or hydrogen bonded to an oxyanion. So things that count as oxyanions, well, those are going to be things like chlorate, chlorite, let's see, nitrate, nitrite, carbonate, sulfate, sulfite, phosphate. All of those things, you see that they're oxyanions. There's oxygen in that polyatomic ion. All of those, if they're bonded to hydrogen, make an oxyacid. So how do we know how to name an oxyacid? Well, it depends on the ending of the anion. If the anion ends in the suffix ate, the acid will have the suffix IC. If the anion, on the other hand, ends with the suffix ite, then the acid is going to have the suffix OUS. So you just need to look at the ending of the anion to know what the acid's ending is going to be. So let's look at some examples here. So let's say we've got H2SO4, ClO2, let's say HNO2, these ones. So if we look at this, first thing I'm going to do is I'm going to identify the anion. SO4, if I look, is the anion sulfate. If it's sulfate, that means it's going to have the ending IC. So when I write the acid name, sulfate becomes sulfuric acid. Again, HClO2. ClO2 is the anion chlorite. Well, again, if it's chlorite, ITE, we're going to change the suffix to OUS, and it's going to become chlorous acid. Same thing with HNO2. NO2 is nitrite. Well, again, ITE, I'm going to change the suffix to OUS, so this is going to become nitrous acid. And you're going to use the exact same technique to go in the opposite direction. So let's do some examples of that, because that's most likely what you're going to have to do when you're balancing equations. So let's say we've got nitric acid. Let's say we've got phosphoric acid. Let's say we've got hydroiodic acid. Let's say we've got phosphorus acid. Okay. So again, when I'm writing out these names, nitric acid. So the ending is IC, so that means that the anion is nitrate. Well, nitrate is NO3 with a -1 charge. So that means its formula would have to be HNO3. Phosphoric acid. Well, the ending is IC, so that means the anion must be phosphate. Phosphate is PO4 with a -3. Well, that means that its formula has to be H3PO4. Hydroiodic acid. This tells me it's a binary acid. Iodic, well, that's coming from iodide. Iodide is just I with a -1 charge. So that means its formula is going to be HI. Phosphorus acid. Phosphorus means we're dealing with the ion phosphite. Well, phosphite is PO3 with a -3 charge, so its formula has to be H3PO3. And that's how you name acids. If you feel like this went a little fast and you need some more information, I highly recommend that you go back to my Chem A videos from Chapter 8 and 9, where I go over all of these naming topics more in depth. Hope this was helpful, and I'll catch you guys next time.